Yeah, let's start, guys. So if we go back to the feature engineering topic, so we have seen basically, yeah, sorry, the missing values concept. So I think we have covered uh, the numerical part and the categorical part, right? How you can encode with mean, median, some random value, of the distribution part, and in the categorical, how you can encode with mode, missing, etc. So now in this session, we are going to see primarily on the K-NN imputer, guys. Okay, so my screen is visible, right? Can someone confirm?
They are visible.
Okay, fine. So now to start with the sorry, K-NN imputer. So this is a bivariate imputation, right? So what is bivariate imputation? So just to give you a quick recap. So earlier, so what all the techniques we have discussed so far and so forth. So those are all univariate. That means what? So if at all, let's say you're having a column, okay? Let's say we have a column C1. So to fill, and let's say it is having some missing values over here and here. To fill these values, so we have considered only this particular column. The method of approach might be different, like whether you have used mean, median, or mode, or in the distribution values, or any other random value, or in random value also we have seen instead of using completely random, filling it from the already existing values. Okay, a special case of the random imputation. So whatever be the method we have used, we have considered only that particular column. We do not care about, let's say, C2 when we are trying to fill the missing values of C1. Agree? So that is all univariate. But now coming to KNN, which is a bivariate, over here, as I mentioned in our first missing value session, so let's say you are having C1, C2, etc. So to fill a particular missing value of this particular C1, so you are going to consider not only C1 but also all other columns. Okay, so in other words, let's say you are trying to consider this particular row, okay, and using all this particular row, you are trying to fill this particular missing value in this row. Okay, so how you are going to do that? What is the relationship between this row and this row, or any other row with this particular row which is having the missing value? We are going to understand. Okay, now since we not study KNN algorithm yet, so now over here KNN, it means that K nearest neighbor. Okay, this is a one of the machine learning algorithm. Okay, famously used for classification purpose. Okay, we not study it. Okay, but I will give you just basic idea what is this KNN about. Okay, so this is called, as I said, K nearest neighbors. Okay, K is just a variable. Okay, how many nearest numbers you want to consider. Okay, in simple words, what does that mean? The basic principle behind this is a particular point's nature can be decided by its neighbors. Okay, that's it. Okay, I'm just giving you just small brief because we are not discussing this algorithm as of now. Okay, but we are just trying to understand its principle. Okay, its principle states that any given point, its nature, okay, or its classification can be decided by considering its neighbor points. Okay, that means what? Nearby neighbors will have similar properties or similar features. Okay, so that's a basic idea. Okay, how many features you are going to consider? Okay, that means just as an example. Okay, for example, let's say if we consider iris. Okay, iris dataset, over there you are having three classes: setosa, virginica, and versicolor. Okay, now let's say all these small dots, okay, all these small dots are from the training data. Okay, I'm just giving you a basic idea of KNN. Okay, let's try to understand. Okay, so let's say you already have 100 input data points. Okay, so 100 input data points means what? You already have, okay, you already have 100 inputs. That means you have all those four values. What are those? Sepal width, sepal length, and petal width. Okay, all those four values you are having, and its corresponding classification, either it is setosa, virginica, versicolor, you're also having this. Okay, like that you are having 100 rows. Okay, like that you are having 100 inputs and their corresponding classification, what to say, categories you are having. Okay, so and let's say you have plotted all these 100 data points, and let's say all the small dots we are seeing over here is one particular, okay, is one particular point, one particular row. Okay, now let's say, now from a test data set you have considered one new data point. Okay, this blue color point you are seeing over here. Okay, let's say this is your new test data set. When I said test data set, what does that mean? It will have only input, right? It will have only input. Okay, we are not going to consider the output, okay, because it is a job of our KNN model to predict the output. Fine. So you're having only input. So all these green data points, let's say you are having all these green inputs, okay, and all this green, let's say there are 100 inputs. Now our task is to classify this blue color. Okay, what is this blue color? This is a test input, okay, which is having only these 4 values, petal, 2 petals, 2 sepal values. Okay, now I don't know whether what is the classification of this. Okay, it could be this or this or this, I don't know. So according to KNN, what does it mean is, so what I'm going to do, I am going to take these 4 values, okay, and I'm going to plot it. And now this is my plotting of this point. Okay, now according to KNN principle, it states that, okay, we are going to consider few nearest neighbors, that means nearest data points, and I'm going to classify this particular data point into one of these 3. And how does, on what basis I'm going to decide? Based upon the nearest neighbors. For example, let's say I'm going to consider K is nearest neighbors. Okay, I'm going to consider 3 nearest neighbors. Okay, now how we need to choose K, and what are the values which are not allowed for K, and how you are going to get the optimal K, all those we are going to discuss in brief when we discuss a KNN model, okay, in detail. But just the K is just the number of nearest neighbors you need to consider. Now let's say you're considering 3 data points. Okay, now this, if you see, okay, let me take a different color. Okay, now if you see, I'm taking 3 nearest neighbors. Okay, now if I'm just circle it, let's say these 3 data points are the 3 nearest neighbors for my test data point. Agree? Test data point. So obviously 1, 2, 3, first dot, second dot, third dot. Okay, these 3 dots are these 3 data points, and each data point is 1 row. That means 1 flower information. Okay, this one is this 1 dot. Okay, it will have all these 4 values. Okay, and its corresponding classification also. Agree? And this data point will also have all these 4 points, 4 values, input values, and its corresponding classification. Same for the third one. Okay, now to classify this new test data set into this one of these categories, I am going to just see what does this classification categories of this. Okay, let's say this is Setosa, this is Virginica, and this is Setosa, for example. Fine. So since the majority is Setosa, I am going to classify the test data set also into Setosa, because there is much probability that the new test data set can also belong to Setosa category, because it is having 2 Setosas in this neighborhood. Agree? Are you guys on track? Okay, guys. Okay, so that's how we are going to consider the nearest neighbors. Fine. So it is just, the idea is just to classify a given data point according to its neighbors. That's it. So now how are we going to apply this concept to our KNN imputer? So the idea is simple. Okay, now we are going to, for example, let's say you are having this row 1, okay, and this is row 2, okay, and this is row 3, okay, and so on and so forth. Now in row 2 there is a missing value, okay, and row 1 there is no missing value, row 3 there is no missing value. Okay, now I'm going to find out, okay, I'm going to find out the most similar row for this row. Okay, most similar row for this row. It's like I'm finding a neighboring row, just like how I'm finding a neighboring, okay, value for this one. Okay, I'm going to find out the neighboring row for this row. How we are going to find out the neighboring row? It's just a distance between the 2 points, right? For example, it is having, see, this is having value 1, okay, value 2, okay, like that. If you're having value 10 values, okay, now here this value is missing, so this row will also have this value 2, like that, 10 values. Okay, so I am going to calculate the distance between these 2 points. And what is the, how we are going to calculate the distance between any 2 given points, guys? Okay, it is, let's say you are having a point, okay, located in the space. Okay, it will have 2 coordinates, obviously, in a 2D space, x1, y1. You're having one more point, x2, y2. Now, what is the distance formula? Simple, square root of x1 minus x2 whole square plus y1 minus y2 whole square. Simple. If you're having multiple coordinates, okay, you need to just add z1 minus z2 whole square. Okay, like that. If you're having 10 values, you need to extend this for 10. Okay, simple math you do, and you are going to get the distance between these 2. Okay, here we are having missing value. You're not going to consider this value, but except this, you're going to consider wherever the values are present. We are going to find out the distance between R1 and R2. Okay, let's say that is D1. Similarly, you're going to calculate the distance between R2, okay, between all other rows. Okay, so overall you are going to overall you are going to find out a row. Okay, overall you are going to find out a row which is most nearest, or let's say you are considering the top 3 nearest rows. Okay, let's say you are considering top 3 nearest rows. Okay, so let's say some R10. Okay, where you will have R10. Okay, you will have somewhere over here. Okay, somewhere over here R10, and let's say some R15. Okay, and some R1. Okay, this R1, R10, and R15. Okay, there are 3 rows you have considered which are very similar to this R2. Okay, very similar to R2. Okay, now just as an example, okay, just to show you, for example, I am considering this. Okay, I am considering this as my R10. Okay, and this as my R15. Okay, now this R10 row will have some value, first value. Okay, this R15 will also have some first value. Okay, now from KNN, using this KNN algorithm, I have found out that this R1, R10, R15. Okay, these 3 rows are very similar to R2 when compared to all other rows. Okay, so I have considered this top 3 similar rows, and now I am going to fill this missing value based upon these values. Okay, because it is missing in the C1 column, so this value will be equal to this value plus this value plus this value by 3. Why 3? Because 3 rows have considered. It's average value of all other existing values. Okay, so it's going to be R1 V1 plus R10 V1 plus R15 V1 by 3. Okay, that will be the most possible accurate value which I can use to fill this missing value R2. Okay, so as I have mentioned, this is a bivariate because I not consider only C1. Okay, I have considered different rows. Okay, I have considered C2 column also, C1 column also, because to calculate the distance, I need all these values. Okay, once I considered all the columns and I use this formula, and I have concluded the top 3 rows. In that, again, I am using these individual values to take the average value and replace with this. So it is in short, I am using almost all the values present in the data set to fill this particular missing value. Okay. Is it clear? Meghana, is it clear? Okay, fine. So yeah, so now let's see an basic example. Okay, let's see an basic example of KNN imputer. Okay, so this is how we are going to import the KNN imputer from the sklearn.simple impute. Okay, and I think you already know these imports. Okay, train test split, you are aware, pandas, numpy. Okay, and this is a simple logistic regression model. Okay, and number 6 is going to be the KNN imputer. Okay, so you already know how we have imported the simple imputer. Okay, in similar way you are going to import the KNN imputer also. Okay, so now as this basic example, I am considering the Titanic data set. Okay, age, class, fare, okay, survive. Okay, so and after that I'm considering the checking the missing values. Okay, and if you see the percentage of the missing values, you are having age is having the maximum, 19% of the values are missing. Okay, now what I'm going to do, I'm dropping the survived column. Okay, and remaining all other columns. That means what? Age, passenger, class, and fare are going to be my X. Okay, which will be my input features, and Y is going to be only my survived column. Okay, and after that, this is the basic train tree split which you are aware. Okay, the main point is how you are going to fill in the missing values. Okay, now as we have seen this KNN imputer which I have imported over here. Okay, there as you can see I'm using a number of neighbors equal to 3. Okay, now this 3 is a variable. Okay, there is no hard and fast rule that you need to always use 3. You can use 2, you can use 3, 4, any number. Okay, that is which you can experiment and find out based upon the accuracy of the model. Okay, but as an example, I'm using 3 over here, and I'm using the distance. Okay, and this you can as I said, you can just go through the KNN imputer documentation. Okay, so which will tell you how you can handle this for different type of data types. Okay, for example, if you see here weights. Okay, weights, I'm going for the distance. Okay, to calculate the nearest neighbor's distance. Okay, and there are different types of distance also. Okay, one is Euclidean distance. You are having non-Euclidean distance. Okay, so this you can go through the documentation, find different parameters. Fine. So I'm using the distance parameter, and after that see, when I'm doing this K&N imputer, okay, I'm just importing this model, okay, and now I'm fitting it on my X-train, okay, I'm fitting my K&N, okay, on my X-train, fine. So once I have fitted it on my X-train, okay, I'm doing the same thing on my X-test also. That means what? Oh, in this step, my missing values got filled up, okay. So here I'm just creating the imputer, okay, I'm fitting this imputer on my X-train, okay, and I'm using the same thing on my X-test also, fine. So, and after that, see, now the missing values filling is done, okay. Now if I use a basic machine learning algorithm, let's say logistic regression, okay, on my X and Y, okay, and this X train TRF, okay, transformed X train is my input, and just my Y train, okay, this Y train is my output, okay, and I'm just fitting and I'm predicting, fine. So if you see the accuracy 71, fine. So now if this is 71, fine. So that means what? Wherever the missing values are there, I have used the K&N imputer to fill these missing values, okay. But as you know, there is no rule that you should definitely use K&N always, okay. There are different types of imputers we have studied, fine. So one other imputer is simple imputer, which you have seen, okay, where you can fill with mean, median, etc. So we'll try to use that also. For example, here I'm using the simple imputer, okay, I'm fitting and transforming and filling the values, okay. Now if you see from this, if you're again building the same logistic regression model, the accuracy is 69, fine. So here you are having 69% and here you are having 71%. So obviously this K&N imputer is performing a bit well when compared to the basic simple imputer, fine. So how you are going to know? Because of the model's accuracy, fine. So like that you can, it's not, so it doesn't mean K&N is going to work well in every case, fine. So it is just one more method. So it is always better to, experiment and find out, fine. So with that, I think we have seen the simple imputer case also, fine. So we have seen these methods, and also in multivariate we have considered the most used one, the K&N imputer part, okay. So I think its usage is very simple. Just import and fit it on the train data and test data, and just test it with a model building, fine. So that's with the K&N imputer. Any doubts, guys? uh, Hello Meghna, you there? uh, okay, 1 second. Okay, okay, fine. So now I would say this is regarding the missing values, guys, okay. So we took a decent number of sessions to cover different types of missing values, okay. So I think it's time to go to the next concept, okay. So the next concept I am interested to discuss is something called as curse of dimensionality, okay. It's called as curse of dimensionality because I need to give you a basic background regarding this, okay. So now in plain words, let me explain it this way. As you know, what is a basic machine learning algorithm? Okay, any model, ML model, what is the job of it? Just to take input, okay, which are also called as features, okay, features, fine, and just give some output, okay. These are also called as predictions, okay. Fundamentally, this is a job of any machine learning model. Agree? So now if you see, features are the main thing over here because those are the input. You can say, you can call features as oxygen to any machine learning model, fine. Now because the predictions are 100% dependent on the features, fine. So that's why there is something called in machine learning garbage in, garbage out. That means what? If you give unuseful features, you are going to get wrong predictions, okay. So you need to be extremely careful to pass while you are passing the features. Agree? Fine. So now, since we are covering feature engineering concept, so it is important to understand features are important, but how much a useful feature is important, okay. In the same way, an unuseful feature is that much unimportant, okay. What I mean to say, if you are passing a important feature, okay, a machine learning model works well, okay. In the place of, along with useful features, if you are adding even one, okay, not so useful feature, it will make the machine learning model to suffer. Okay, it is going to it will make the machine learning model to suffer. Why? Because over here each feature is considered as one dimension, guys. Okay, one dimension. Okay, one dimension. Why? Because just now we have seen in when I am considering a distance between 2 points, okay, if there are only two values, okay, see, if there are only two values, for example, let's say age and fair, okay, age and fair, there are only two values, okay, this will have some value, okay, x1, okay, this is having y1, okay, and this is having x2, y2, okay. So if you want to calculate the distance, what will be the distance? It will be square root of x1 minus x2 whole square plus y1 minus y2 whole square. Agree? Now, if I add one more column, let's say gender, okay, it will be that will be one more z1, z2. Okay. Now you are going to add x1 plus x2 whole square plus y1, y2 whole square plus z1 minus z2 whole square. Agree? That means what? Why I am adding one more thing? Because I'm considering this as a new dimension. Okay. This is 2-dimensional. If you add one more column, that will become 3-dimensional. That means each column, okay, one column is considered as equal to one dimension. Okay. So the more number of columns you are using, that means it is going to operate in n-dimensional space. Okay. N columns equal to n dimensions. Okay. That's why columns are very, very important, guys. Okay. As I said, even if you remove 5 to 10 rows, that is not going to affect, okay, much. But even if you remove one column, it's going to affect, because one column is one feature. That means it is having very significant amount of information about a data set. For example, if you remove this gender column, obviously you are missing a lot of useful information. You are missing whether it is a female or male. Okay, agree? So even the age column, even the fair column, agree? So that's why every column is important. Okay, at the same time, it is also important not to include any, okay, unuseful features. Okay, it is also important not to use any unuseful features. Okay, so that's why the curse of dimensionality means, okay, so it is having, if you're passing too many features, okay, if you're passing too many features, okay, too many features, so then any machine learning model will suffer. Okay, any machine learning model will suffer to predict the output. Okay, now what are these too many features? Okay, if by evidence, if you're able to see some statistical evidence that all the features which you are passing to a model, okay, if those are perfectly useful, okay, they are having perfect correlations, okay, with the output variable and with the different techniques which we have seen, okay, by plottings or okay, or some feature engineering techniques where, as we have seen, okay, correlations, etc. Fine. So if you are confident, then you can use as many features as you want. Okay, but I'm speaking about those features which are not required to use. Okay, so even if you use less number of features, even if you use the features which are required, if I mean to say, let me come again. Okay, even if you're not using the features that are really important, that is also wrong. And even if you are using the features which are not required, that is also wrong. Okay, like, did I confuse? Let me say again. Even if you are not using the features that are really important, that is also wrong. Even if you are using the features that are not important, that is also a wrong thing to do. Agree? So mainly the curse of dimension deals with using unnecessarily lot of features. Okay, so that will obviously create major problem issues. Okay, why? Because see, when you are doing, for example, even the simple example in the missing values example itself, okay, here we are considering distances, right? So let's say instead of 5 features, okay, let's say instead of 5 features, okay, you considered 3 more features, okay, 3 more rows, okay. And now what will happen? You need to calculate the distance of each and every row with these new 3 columns. Okay, now if you see, it requires so much of calculations, okay, which will directly impact the computation, okay, memory, okay, resourcing, okay. And now all these are linked to something called as cost management. Agree? So unnecessarily you are taking the burden, okay, and you're not getting any output from these features. Okay, then why to use those? Okay, so now that is a problem, okay, that which we are having, and this comes under the heading of curse of dimensionality. Okay, so if you are increasing more dimensionality, then obviously that is going to be curse on the model. Okay, so, and what is a dimensionality? As I said, just each feature is considered one dimension. Okay, one feature, one dimension. Okay, fine. Now just to give an example, okay, so for example, let me take an example of let's say there is an use case called as digit classification, guys. Okay, there is a use case called as digit classification. Okay, so over here, what happens is, let's say you are having, okay, I think I have shown you digits classification, right? So for example, if you see yeah, so for example, yeah, yeah, so over here, yeah, if you see, this is my input data, okay, input feature, okay, one image, okay, this is just a simple image, and this image is going to the input, this image is going to the input, okay, and the prediction should be the number, okay, whether it is 5 or 6 or 8, okay. So this is obvious, this is 5, okay, but the point is, even if this curve is distorted or it doesn't really look like 5, still the model should be able to predict it as 5, okay. So now the point here is, if you see, okay, let's say this is a 24 by 24 pixel image, okay. So what do I mean? It is a 24 by 24 pixel image, okay. So that means you will have, you are going to, each box, okay, will be 1 pixel, okay, like that you are going to have 24 over here and 24 over here, okay. That means in total you will have 24 and 24, 576 boxes, okay. In total you are going to have total 576 boxes, okay. Now each box is going to be one feature, okay. Each box is going to be one feature. That means overall you are having 576 features, okay. So overall you are going to have 576 features getting, okay. This is one feature, this is one feature, like that you are having 24 in one line, okay, like that more 24 you are going to have, overall 576, okay. That means in point 1, okay, data point 1, it is going to have, okay, 1 2 like that, 576 features are going to be present, okay. And the last column is going to be the y variable, okay, whether it is, what is the number, whether it is 1 or 2 or 3 or 5. Let's say in our case this is 5, okay. Now the point here is, let's say in this example, as you can clearly see, most of the image is white color, okay. So even if you don't consider this particular white part, it is not going to make any difference, okay. Agree? Even if you don't consider all this white part features, okay. So this, as I said, every box is going to be one feature, okay. So even if you don't consider many of the features, okay, there are so many features over here in this white space, even then it is not going to make any difference at all for our model, okay, because there is no useful information available in these white spots, okay. So but still, if you are going to use all the 576, okay, if you are going to use all the 576 values, the system or the model should consider, process and consider all these 576 inputs in the output prediction, okay. But the same output prediction can also be achieved, okay, without using these white boxes, okay. Even instead of using, okay, just as an example, instead of give me a second, okay. So instead of using all these whites, this whole, sorry, okay, instead of using this, okay, if you are able to consider just this much of the box, okay, a few more white boxes, okay, because you cannot exactly pick and choose, okay, a few white boxes is fine, okay. Still you are going to achieve the same result, okay, and this is way better than considering the whole box, okay. But if you that's what I said here, what I was saying here, useful, if you are not considering the useful features, that is also wrong. And if you are not, if you are considering the unuseful features, that is also wrong, okay. So for example, if you are just considering this particular box, okay, you are using a lot of useful information, see, then you are not considering all the required input features, okay. This is also wrong, okay. But if you are considering the whole image, okay, where you are having a whole lot of white spaces, that is also wrong, okay. So taking what is less compared to the required one, that is also wrong, and taking what is more compared to the required one, that is also wrong, okay. So in first case, you will not be able to get decent predictions, okay, at all, okay, in second case, it will be unnecessary waste of your resource and money, okay. So that is the example of the cursive dimensionality. That means what? So let's say this small box, okay, this small box, okay. So if you consider each and every small box, let's say it is having, there are 200 features over here, okay. So overall there are like 576, or it is 270, okay. Now what are the leftover boxes? 376, okay. So 376 features are belonging to this white part, okay. So which you can ignore, fine. So the whatever the prediction you are going to achieve with this exact 200 features, you are going to achieve same thing with this 576 also. Then why I will go with why I will choose 576? I will just go ahead with 200 features, right? Because that is where exact my input is present. Agree? So the problem which we are trying to focus here is when we are considering the features which are not actually important, okay, but still if you are considering and passing to the model will spend its time and energy, okay, to find out multiple things, okay, using on that features, okay, for the output prediction, okay, which is not worth, okay, to put it in simple words, okay. So that's called curse of dimensionality, okay. That's called curse of dimensionality, okay. You are unnecessarily increasing the dimensionality, okay, without any positive impact on the output, fine. So is the concept clear? Are you getting a sense of what is curse of dimensionality? Let me know in the comments.
Yes, sir.
Okay, fine. So now since we understood what is curse of dimensionality, so obviously we understood that it is not okay to use more number of features, okay. So now one idea is, so, and second point is, even if you're having, let's say, even if you're having, let's say, useful features only, okay, but still if the number is high, let's say you're having 50 features, okay, even if you're having 50 features, all are important only, okay, but still since the number is high, it will still not a good way or ideal way to pass this number of features for a model building, okay. So in that cases, what you're going to do over here is you can use some methods, okay, you can use some methods, okay, to create some features, okay, less number of features when compared to 50 features, okay, so that it will be more easy for the model building, okay. One, those particular technique is called PCA, okay. It's called principal component analysis, okay. It's called principal component, okay, it's called analysis, okay, in which you are going to, from the given number of features, let's say you're having 50 features, okay, you are going to analyze these and come up with very few number of features, let's say 3 or 4 features, okay, 3 or 4 features, okay, and these will represent, okay, these 3 or 4 features will represent these 50 features, and you can use just these features for your model building, okay. So at first hearing, you can feel it's a bite of surprise that how you can compress 50 features into just 3 or 4 features, okay. If it is really possible with the just 3 and 4 features, then like what is the use of using the 50 features? Why we are having the 50 features in the first place, okay? When we are able to convert all the 50 features into just 3 or 4 features, okay, then it is obviously a great thing to hear, right? Okay, but what is going to happen to other 46 or 47 features, okay? So these are some interesting questions which I will be answering, okay. And what are the pros and cons, okay. So it is going to, obviously, if you want something, you need to lose something, right? So when you are gaining this particular advantage, that when you are gaining from 50, when you are able to reduce 50 features to 3 or 4 features, obviously you need to lose something, okay. What is that you are going to lose? Okay, you are going to lose the readability, okay. That means the new features which you are going to create, right? So those are not human readable, okay. So all these pros and cons we are going to discuss when I specifically discuss this concept called as principal component analysis. But this concept is very, very useful, okay, when you are dealing with something called as specifically curse of dimensionality, or in some cases even when you are having the features are useful features, but still if the number is too high, then also you can consider this PCA, okay. And you can train the model on these features, okay. And the features which come out of this PCA are called principal components, okay. They are called principal components, okay. So all these things which we are going to discuss when I consider this PCA concept, okay. Fine. So I would say that's all regarding the curse of dimensionality and feature creation, okay. And I would say going back, okay, I think we have seen what is this feature transformation, Okay, in feature transformation itself, we have seen multiple things. Okay, how to handle missing values, handling categorical values, outline detection we have seen, feature scaling we have seen. Okay, and coming to feature construction, here we are going to just create features manually. Okay, so it is as I said, it is not related to any algorithm or such thing, guys. Okay, you need to just create features manually. That means as a simple example, I'm not going to show any example because it is very basic, okay, which you can try it yourself. That means, for example, let's say you are having let's say you're having Mr. Karthik, okay, and let's say you're having Mrs. Meghana, okay, etc. like that. Okay, so you can just create features manually from this. That means if you want to just separate this what do we call this, okay, addressing, okay, addressing of the user, okay, you can create a separate column for this. And let's say if you're having Karthik and some other surname, okay, Meghana and surname, okay, you can create 3 features, okay, from one single feature. Okay, so here you are just creating features manually. Okay, and obviously you need to have some domain knowledge how you can create. For example, as I said, if you want, instead of having in the Titanic dataset example, you are having passenger or you are having something called as sibling and spouse. Okay, sibling and spouse, and also what do we have, number of kids. Okay, you are having a field something called siblings or spouse and number of kids. Okay, you can just merge these two and create a new column called as family members. Okay, family members. Okay, because if you think instead of 2 columns, okay, 1 column is going to serve the purpose, you can use this 1 column. Okay, here you are creating the features manually. Fine, it could be splitting a given feature or merging 2 features. Okay, and create. Okay, so this is just a manual based upon your domain knowledge and your thought process. Okay, no algorithm involved. Fine. And second thing is related to the feature selection, guys. So third things, feature selection is actually you're going to select features from for a model, right? So here I'm going to discuss this, okay, not separately, but along with certain model, okay. And after covering few models, okay, I'm also going to show you how you can do this with some machine learning models itself. Okay, there are some machine learning models which will directly select the features for you and let you know. Okay, that means first we are going to train with all the features a model, and after that model is going to tell you which features are most important, so that we can use only those features and train again the model. Okay, so this I'm going to show you with an example, okay, when we are discussing the models. Okay, and the other thing is feature extraction. Okay, over here that means we are extracting the features. Okay, so this is the concept which is related to the things which I've just discussed. Okay, how we are going to extract the features. Okay, one concept is PCA. So here you are going to, from 50 features, we are going to extract only 3 or 4 features. Okay, how you are going to do that. Okay, and there are some other techniques also which I will be discussing post the PCA. Okay, and yeah, I will see if we are having any other feature extraction techniques also. Fine. So this is just an overview, guys. Okay, so this is just the basics of the feature engineering at a high level. Okay, but once we cover few of the models, and once we take some example, right? So then I will show you step-by-step process of feature engineering. Okay, with an end-to-end example. Okay, so this is just you are collecting different concepts and putting in a bucket. Okay, and how to use it in a pipeline. So we are going to see in later point of time. Fine. So yeah, I would say that's all for today's class. Okay, because I want to cover these like general concepts. Okay, post this what I'm going to do is next class we are going to start our ML model, guys. Okay, because I think it's now high time to start machine learning models. Okay, so I'll start machine learning model. So first model will be obviously the famous regression model called as linear regression model. Okay, I'll cover a bunch of machine learning models. Okay, and after that we are going to come and cover something called as PCA. Okay, and with examples. Fine. And then we are going to cover again a set of models. Okay, so as I said, we are going to cover basically 10 machine learning models. Fine. So if I just go back, type of MLs, just give me a second. Did I cover? Where did I cover? Of ML, yeah, in supervised, unsupervised, semi-supervised. Where did I? Fine. Anyway, I'm not able to find it. Okay, that's fine. So as I said, we are going to cover 10 top important machine learning models we are going to cover. Each model we are going to cover with detail, intuition, okay, basic theory, okay, and practical code and some examples. Okay, so with these four sections, I can be sure that we are going to have decent knowledge on each and every machine learning model. Fine. So once we have done with these machine learning models, right? So 10 models, and along with apart from this 10, we are going to consider PCA concepts also. Okay, so once we are done, I would say major chunk of the machine learning portion will be covered. Okay, and post that, just give me a second. For example, if you see over here, we have done with these plottings. EDA we have considered, okay, and EDA is not an just one. I would not say, I would not like to call it as a separate section. Okay, it will come on and on when we are discussing different models, right? So in every part of our data science or mainly machine learning journey, right? So you will come across this EDA, okay, and every time you are going to discuss data set, you might learn a new types of feature engineering or EDA techniques, which I will be showing, okay. And as shown, so once we are done with this machine learning part, right, so we'll be done with the most of the ML stuff, okay, and then I'm going to discuss I'm going to then discuss few end-to-end machine learning projects, okay, and then I will come back for the NLP, okay, and then you will have some interview sessions, okay, fine. So yeah, that's all, guys. That's all for today, I would say. Okay, so I hope you are enjoying the session, guys. Okay, it might I agree it might be a bit dry, okay, because these are some general concepts, okay, but from once we start the models, right, so I can give guarantee that it's going to be more interesting when compared to other classes, okay. So because you will be it will be good stuff of theory, and you will see the practical. There you will actually see why you are doing all this, okay. All the concepts, as I said, all the concepts what you are studying, etc. So ultimately they should help you, okay, they should help you to build a particular ML model. Fine. So everything we are doing, right, so that is because of some model, to build a model, to give some predictions, okay. So what all we have studied, okay, so that will be in the anticipation of these models, okay. So this we are going to study in our next class. Fine. So then you are going to connect few more dots, okay, and that should be useful. Okay. Fine. Are we good? Any doubt, guys? Let me know in the comment section. Okay, fine. So I think we are good. Fine. Let's meet in our next session. Thanks, guys.